Consider an age-structured population of unicorns made up of juveniles and adults. So within the unicorn population, there's juvenile unicorns and adult unicorns. So we sort of have it could count as two separate populations, but as we're going to see, they will influence each other. Each adult we count in 1 year produces, on average, 7/3, so that would be 2 1/3, so just a little more than 2 juvenile unicorns counted for next year. Of course, it's on average. How can you produce 1/3 of a unicorn? That's just silly. Everyone knows unicorns come in whole numbers. Anyways, okay, so getting back to the question, each juvenile we count in 1 year survives to be counted as an adult unicorn in the next year with a probability of 1/3. Okay? So only 1/3 of the juveniles in a given year, make it to adulthood. Life as a unicorn must be tough. Anyways, finishing up, finally, half of the adults we count in 1 year survive to still be adults next year. So they live. So half of the adult population just vanishes or magically bursts into pixie dust or something at the end of each year. But half of the adults make it, half of them don't. All right. Here's our question. Determine the long-term ratio between the number of juveniles and the number of adult unicorns in this population. Okay, so our answer is going to be a ratio like there's 3 juveniles for every 1 adult, or there's 2 juveniles for every 5 adults in the long run. And when you're thinking long term or long run, you're thinking things like limits. You're thinking things like in this case, because we've got 2 populations that are influencing us, we can probably set up a system of equations. There's probably a matrix running around, and so we might be looking at eigenvalues, eigenvectors. In particular, for long-term behavior, we'd want to be talking about dominant eigenvalues. But that's getting ahead of ourselves. Let's see if we can turn the given sort of wordiness of the problem into a proper model. Then we can start talking about long-term and generalizations and things like that. Okay, so here's what we're going to do. We're going to have 2 populations. So we're going to say, let's let x of t, it doesn't have to be x, it could be p for population, or it could be, actually, let's have some fun. Let's make it a vector u of unicorns. U of t is the pair of populations, so we'll have u1, and that'll be the juveniles in the teeth year, and then we'll have u2 be the adults, the adult unicorns in the teeth year. Okay. So over time, these 2 populations change, but they influence each other. Juveniles grow into adults. Adults produce new juveniles. Okay. So let's see if we can set up a model. How do we get next year's populations from this year's populations? Okay. And it turns out we're going to use a nice little matrix, a little transition matrix. Okay, so sometimes when it comes to setting up the matrix, it can be a little bit hard. We're gonna have to reread the question a little bit, but it can be helped out a little bit if you keep out instead of writing them with just the little harpoon hat. You actually keep out, okay, juveniles this year, adults this year, and then we're calculating the juveniles next year and the adults next year. Okay. Because setting up this matrix, we really have to remember how matrix multiplication works. So, to calculate the juveniles next year, and sometimes it's helpful to write things out. So, juveniles next year is what? It's none of the juveniles this year, because they either die off or explode into fairy dust or whatever, or run off chasing leprechaun. I don't know what happens to them, but none of them continue on being juveniles. They graduate into adults. Okay, so 0 of the juveniles, and then each adult. So from the current unicorn population, the current adults, produces on average 7/3 of a juvenile for next year. So 7/3 times the adults this year, and that produces the juveniles next year. Okay, so we can then say, okay, well, the juveniles next year, so that's the u1 in the xt plus 1 vector, and that's 0 times the current juveniles plus 7/3 times the current adult unicorns. So how does matrix multiplication work? The first row is used to calculate the first component of the next cycle or next year's unicorns. And you take the first number will match up with the U1 when you do matrix multiplication. The next number will match up with the U2. If there was like a third population of elder, wizened unicorns, then we'd have a third value for the U3 there. But okay, we can just then lift these numbers. Okay, this will be 0, this will be 7/3. Similarly, not the juveniles, we just did the juveniles, the adults next year. How do we get adults next year? Well, I think it's a third of the juveniles turn into adults. Yeah, survive. So the juveniles in 1 year survive to become adults 1/3, with a probability of 1/3. So that means 1/3 of the juveniles should survive. So 1/3 of the current number of juveniles. But then there's also the adults who survive, and the adults survive half the time, or half the adults survive, so half of the current adult population, and we can slot these numbers into place here. So we get our matrix for how the population changes. Next year's population is 0, 7/3, 1/3, 1/2 times the vector representing this year's juvenile and adult populations. Okay. Were we given an initial population? We're not. Probably because the initial population doesn't matter for long-term things. Like, for example, if this matrix of transition, or this way of the unicorn populations changing, if it's in some way degenerate, if they're destined for extinction, that won't matter with how many unicorns there are at the start. If you start with a large number of unicorns, yeah, it'll take a while to go extinct versus starting with a small number of unicorns, but it's all about the matrix. So if they're going to go extinct, it's based solely on the matrix, not about how many unicorns we start off with. Similarly, if the population is going to explode, it has nothing to do with the starting population. If you're going to get an infinite number of unicorns after a while, it doesn't really matter how many started with it. It's just going to keep going. So we weren't given any initial population, so we're just left to analyze this recursive model for our unicorn populations. Okay, so what should we do? Well, we would like to understand UT as an expression in terms of t. So in terms of just t. So right now, if I wanted to calculate how many unicorns in each adult and juvenile population 100 years from now, I'd have to multiply by this matrix 100 times. That's really tedious. Matrix multiplication takes a while. So it'd be nice if we just had some formula that said, there'll be 100 squared juvenile, like t squared juveniles, and then t plus 5, so 100 plus 5 adults. Right? If we had some formula just as functions of t for our sequence here, that would be fantastic. All right, so that's what we're going to go for. Fortunately, there's something really nice. If we have a very basic matrix recursion model like this, all you got to do is find the eigenvalues. We'll say maybe lambda 1, lambda 2, lambda 3. Well, there's only 2 of them. And for each one, you have a corresponding eigenvector. We'll say v1, v2. Then in general, ut is a sum of multiples of powers of eigenvalues times their corresponding eigenvector. Okay? That is just general theory we have for models that look exactly like this. Next year is current year times this transitioning matrix that has constant numbers in it. Okay? So in order to use this model, we will have to do things like find our eigenvalues and then find corresponding eigenvectors. Now, since we weren't given an initial population, we won't actually be finding A's and B's. And as I said, we'll probably have to look for dominant eigenvalues and go from there and sort of work on our long-term behavior based on that. Okay, so let's jump in. We'll take our matrix 0, 7/3, 1/3, and 1/2, and let's start analyzing it. Let's get a characteristic polynomial. So for a 2x2 matrix, there's a nice little formula. Characteristic polynomial is lambda squared minus the sum of the two numbers along the main diagonal. Fancy term for that is the trace of the matrix. And then plus the determinant, which is product along the down arrow, so 0 times half, so that's 0, minus product along the up arrow, so 1/3 times 7/3, so that'll be minus 7/9. So we get lambda squared minus a half. Oops, I forgot my lambda in there. So minus a half lambda minus 7/9. There we go. So now, to find eigenvalues, they are just the roots of the characteristic polynomial. So we set the characteristic polynomial to be equal to 0. And we say, all right, what lambdas make this work? Now, with fractions, we have options. If you can just look at this and say, oh, yes, I can factor that into lambda minus this times lambda plus that. Great, fantastic. I'm looking at these, and I'm not so sure that I can. Maybe something like minus a third, minus a sixth, or something. I'm not entirely sure. Another thing we can do, you can always use the quadratic formula. That always works, guaranteed. That even lets you find complex solutions. Another thing we could do with fractions specifically is we could come along and get rid of the 2 and the 9 by multiplying everything by 18. Now, the reason you might not want to do that is then you're going to have an 18 up front here, and that might make things a little difficult to factor. It sort of depends on your skill level, your familiarity with certain things. So we might say, well, could I factor something like this? Right? Could I do something like that? And, maybe 3 lambda minus 2, and then like 6 lambda minus 7, or something like that. In fact, so the reason I chose 3 and 6, 18, 2 and 7, 14. Signs here would need to change a little bit. And then, let's see, 6 and 2, 12. Oh, yeah, I think I did. That was just an idle guess. If you're not a fan of idle guessing, or whenever you idle guess it doesn't work, quadratic formula. Go with quadratic formula. But yeah, 3 times 7 is 21. So 3 times negative 7, that's negative 21. And then we're going to add on 12 lambdas, and that should give me my minus 9 lambdas. Oh, that works. Fantastic. So we managed to factor it. Now, I hear you saying, well, you got lucky. I did. I really did there. That wasn't planned. So let's, just for fun, let's do the quadratic formula and show you that, yeah, that always works. So we'll go back with the original expression we have here, because I don't want to deal with dividing by 36 or something like that. So lambda here is negative b, so that's the 1/9, plus or minus b squared, so negative a half squared is 1/4, minus 4ac, all over 2a, so that's all over 2. So that's 1/2 plus or minus, we got 1/4 here, minus 4 times minus 7, that's going to be plus 28/9. We're going to need a common denominator here of 36. I'm going to move this over to the other side. If you want, you can just skip past this. If you're going to say, no, I expect I'll get lucky too, go for it. We'll have 9/36, and then multiply top and bottom here by 4. 28 times 4. No sense reaching for a calculator. We don't need that. 112. So 112. 36 there. Yeah, that should all work just fine. And then we can now, over 2. And then we can add 9 plus 112. Oh, look at that. It's a very nice number. It's 121. 121 is just 11 squared. 36 is just 6 squared. So we can square root and get 11/6. And so now we have 1/2 plus or minus 11/6 all over 2. I'm going to divide through the 2, so this is 1/4 plus or minus 11/12. So 1/4 plus 11/12, and then 1/4 minus 11/12. But 1/4 is 3/12. So 3 plus 11, 14. 14/12, that's 7/6, which you can see corresponds to this lambda here, 7/6, where we need the factoring that I got lucky with. And then 3 minus 11, that's negative 8/12, which divide by top and bottom by 4, you get negative 2/3, which does correspond to this one. So get lucky like I did. Be amazing with fractions at the start. You could have skipped all of this, or again, you can always go quadratic formula. Always, always, always works. Okay? But there we go. So we now have our eigenvalues. 7/6, and minus 2/3. Okay. Now, remember the question. We're looking at long-term behavior. So let's talk about dominant eigenvalues. The dominant eigenvalue is the one that has the biggest absolute value. So yeah, 7/6 is bigger than minus 2/3, but that's just because this is a negative number, right? So make them both positive, right? Slap some absolute values on each. You don't need it for the 7/6. But 7/6 is bigger than 1. It's more than 6/6. And minus 2/3 goes to 2/3. That's less than 1. It's less than 3/3. So 7/6 is the dominant eigenvector. And what that means is in the long run, when you have a sequence, in this case representing 2 unicorn populations, a sequence modeled by exactly the sort of thing we're looking at, just multiplying by a single matrix there, then in the long run, so as t gets bigger and bigger as the years go on, ut is approximately some multiple, doesn't matter what, but there will be some multiple, your dominant eigenvalue to the power t times an eigenvector associated to that eigenvalue. Okay? So in the long run, u of t is going to look something like this. Some multiple of 7/6 to the t times an eigenvector for 7/6. And so if we want the ratio in the long run between juveniles and adults, we really just need to find this eigenvector here. Okay? And the constant here doesn't even matter, because when it comes to, let's for a moment, let's just say the eigenvector was 1, 1. Actually, we'll say it's 1, 2. Okay? Whatever the c is, you're going to get c times 1 and c times 2, so c to c, and so c to 2c is the same as the ratio of 1 to 2. They're in the same proportion, so the multiplying by c is not going to matter at all. So really all we're after is what is an eigenvector associated to 7/6. So we can actually ignore minus 2/3. Okay? So that it's nice when that happens and things narrow down. So take our original matrix and we'll subtract off 7/6. I think it was a 7/3 up here. I think it was 1/2 and 1/3. I will go back and double check because I don't want to. We're almost done, and I don't want to make a mistake. Yep, 7/3, 1/3. Okay. So this matrix is minus 7/6, 7/3, 1/3, and then this is 3/6, so that'll be minus 4/6, which is minus 2/3. Okay. So there we go. That corresponds to our original matrix A minus the 7/6 times the identity. So what we're going to do is we're going to set up a nice little... we're just going to use the definition of an eigenvector and set up a way to find eigenvectors. So this matrix times v1, v2 being equal, giving us 0, 0. As long as v1 and v2 aren't 0, we'll have an eigenvector, and then that will give us the long-term proportion between the juveniles and adults. Okay? Even though we won't have an actual formula because we didn't have a starting population, it's fine. It'll all work out. So matrix multiplying, we get minus 7/6 v1 plus 7/3 v2 equals 0. And then the second one, 1/3 times v1, so 1/3 v1 minus 2/3 v2. Okay? Now it's hard to see, but the first equation is a minus 7/2 times the second equation. So these two equations are both saying the same relationship between v1, v2. You only need to solve one of them. I'm going to go with the one that to me looks easier. Okay? It's got 1/3 and everything like that. So we're going to bring the 2/3 v2 over to the other side. I'm going to multiply both sides by 3. v1 is 2 times v2. Okay. And so all you need, let's let v2 be equal to 1. So v1 is then going to be equal to 2. And so that means 2, 1 is an eigenvector. Right? It's not the only one. 4, 2. -10, -5. But there we go. There we've got an eigenvector for our dominant eigenvalue. And so what does that ultimately mean? In the long term, or I can't remember if the question said long term or long run. Long term or long run. Doesn't matter which one. Actually, I'll stick with just long term. both populations as a vector are going to approximately be some multiple of your eigenvalue to the power, the dominant eigenvalue to the power t times this eigenvector that we just worked out. And so the juvenile population is going to be the first component, so that'll be 2 times c, 7/6 to the t, and the adult population is going to be c 7/6 to the t times 1, so c 7/6 to the t. We're not interested in any specific values. The question asked, what is, I'll go back and double check, what is the ratio between the number of juveniles and the number of adults? So it's really just going to be 2 juveniles per every adult. Right? This gives you the juveniles. This gives you the adults. And we can even set up the ratio 2c 7/6 to the t, 2 c 7/6 to the t. The nice thing about ratios, like 6 to 4, if you divide both sides by the same number, you get the same ratio. So we're just going to divide both sides by the c, because it's irrelevant, and we're going to divide both sides by the 7/6 to the t, and we're left with a ratio of 2 to 1, which actually we could have worked out as soon as we got this eigenvector, as soon as we got this relationship, really, between juvenile and adult. Okay? But there we go. So our final answer is a 2 to 1 ratio, or you could say 2 over 1. I wouldn't simplify that to 2, but plenty of people do. But 2 over 1 or 2 to 1, I think this is the usual way a lot of people write ratios. But there we go. Juveniles to adults, 2 juveniles for every 1 adult in the long run. Okay? And there we go. So that gave us the long... It was long term. Okay. I didn't know if it was long term or long run, but there we go. Our final answer, 2 to 1.